My name is Shaofeng and I'm from Peng Laboratory. Today I will be talking about our recent work, Yes 1-bit flip mentors. Okay, let's jump straight into it. It is well known that AI models are vulnerable to various attacks, for example, adversarial attacks, poison attacks, and backdoor attacks. All of these attacks originate from the AI models themselves, rather than from the environment they are deploymented. However, AI models run on hardware, and the hardware can also be attacked, for example, fault injection. Existing works has explored that injecting faults into weights of DNN models. DNN weight models are loaded into memory cells. During runtime, Rowhammer bugs or memory cells can be exploited to manipulate data storage in memory. Such modifications significantly decrease or increase the weight value due to the influence of the exponential part. The compromised model weights lead to low inference accuracy, usually less than the random guess. However, as is well known, DNNs exhibit robustness of their weights. In other words, a small proportion of model changes does not significantly affect the inference accuracy. Thus, existing work requires the flipping of tens of bits of model weights. However, it is challenging to implement attacks that simultaneously flipping multiple bits in memory. So, can we just flip 1 bit? Our answer is yes. We can flip yes 1 bit is matters. In contrast to prior work, our attack targets the machine learning libraries. Instead of DNN model parameters, this slide gives an overview of our attack. It is compromised 3 steps. The first step is search vulnerable instructions in machine learning code libraries. The second step is relocate the founded vulnerable instruction to the matched flip above physical page. In the third step, we exploit the Rowhammer bugs to flip the targeted bit. All of those attacks operations run in the attacker process with no privileged user, and thus is stealthing. Okay, let's elaborate more on details. The first step of our attack is to find the vulnerable instruction in machine learning code libraries. So we analyze the machine learning code libraries as a control flow graph. In a control flow graph, bridge instructions presented as edges, and it controls the execution logic of the whole program, and thus have the greatest impact of the execution logic of the program, which indicates that we should choose those branch instructions as the targeted vulnerable instructions. When we step into a specific instruction, an instruction is compromised 2 parts, OP code and the arguments. To maximize the attacker performance, we choose the OP code to flip. In particular, by utilizing the OP code's Hamming distance, we can define the set of adjacent instructions that contains potential vulnerable malicious instructions, taking the GE instructions as an example, with the constraint that the OP code of adjacent instruction of GE instruction should differ only 1 bit. We can identify many instructions within the instruction set. For example, XOR, push, halt, and etc. Note that not all these instructions are considered as adjacent instructions, as they must satisfy semantic validity. For instance, XOR instructions is not an adjacent instruction due to its differing parameter list. The lines in the figure represent the set of adjacent instructions, from which we can choose one as a vulnerable instruction. When we determine the targeted vulnerable instruction, the next step is putting this vulnerable virtual memory page to the flippable physical page, and then triggering the Rowhammer bugs to flip the targeted bit. This process also includes 3 steps. First is memory profiling. Second is page relocation. The third is Rowhammer bug exploitation. Firstly, we scan the DRAM to find the flippable position. Second, we extract the attacker pattern of the vulnerable instruction based on the offset within the code page and the flipping direction of bit flip, and match the attacker pattern in memory cells. After obtaining the matched position, we utilize memory relaying tag to achieve the relocation of the code page. After obtaining the matched flippable position, we utilize memory relaying tag to achieve the relocation of the page. At last, the attacker leverages the Rowhammer bugs to achieve deterministic tampering of targeted bit. This is a demo to show how our attack works.
H. We find and locate vulnerable branch instructions in the machine learning library. We run an element-based search algorithm. The algorithm scans the library source code and lists all the exploitable branches. For each branch instruction, the algorithm creates a new Poisson image of the library with a reverse branch control logic. Then the algorithm evaluates a deep learning model against the Poisson library to find out the adversarial effect on the model. In this demo, we iterate over the 120 branches in the matrix multiplication function. In the evaluation process, we observe 4 kinds of faults, namely model failure, invalid output, denial of service, and process crash. After that, we look into the evaluation results. As we can see, the 4 types of faults span over the 120 branches. Here, the branch index refers to a specific branch instruction. Here we give you a closer look at the faults. We show you the results of 5 library images. 3 of them are model failures, and 2 of them are process crashes. Now the idea is we exploit the Rowhammer bug in the host machine to reproduce the faults found in the offline stage. Now we come to the online stage. In this stage, the attacker runs as an unprivileged process, while the deep learning model runs as another process. As we've mentioned, in this stage, the attacker exploits the Rowhammer bug to reproduce a model fault caused by the Poisson branch instruction. So the attacker first profiles the Rowhammer bug layout on the host machine. We can do this with the Rowhammer.js tool for DDR3 or the TraceBus tool for DDR4. These tools produce a list of bugs in the memory. Now we look into the Rowhammer bug list. There are tens of thousands of bugs on the host machine. Some of them can be exploited for our purpose. Now we come to the final part of our attack. Before the attacker takes any action, we assume that the deep learning process is already running on the host machine. Now we launch the real attack. In the attack, we select the type of fault to our interest. Here we choose inference failure. The attack first matches the flip patterns obtained from the offline stage with the online Rowhammer bug list. Here, the inference failure fault matches 88 bugs. Then the attack runs a page relocation procedure called memory relaying, trying to land the branch instruction to a page with a matched Rowhammer bug. The relocation process depends on the kernel's page management module, so the time expense has a bit of uncertainty. When the instruction is finally landed on the Rowhammer bug, we hammer the instruction. The hammering takes an instant effect as the exploit takes place in the memory. We can find that the next batch accuracy immediately drops from 90% to 6%. This is a successful end-to-end attack for the inference failure fault. The attack can also cause other types of faults, which are not shown in this video due to the time limit. We find and locate vulnerable branching.
Okay, this slide reports the experiment evaluation of 10 different classification tasks, or 4 different benchmark datasets and 4 types of network architectures. The experiment results confirmed the effectiveness of our attacks. This slide shows that our attack has transferability in terms of fault types, which means it can be same fault types appear across models and datasets. Compared with other works, our work only needs flipping 1 bit to achieve the better attack performance. Thank you for your listening. More insights, code, and data can be found in our website. Thank you.